Good evening, folks. We are just about ready to start tonight's Advent of Code stream. As always, we're going to be solving these puzzles in C++. Tonight we're doing Day 12's puzzles. We have only a couple minutes left before the puzzle unlocks because we're starting a little bit late this evening. So the first thing I'm going to do, just in these couple of minutes remaining to us, is set up our little skeleton for Day 12 solution here. Make a directory for that. Make this part1.cc file for our main function and put our main function in it. There's our minimal C++ program. I will now, as we've done every day, make a build file to show the Basil build system that I'm using, how to build it. Okay, and now we will go ahead and build and run that minimal program. Okay, and we're good to go. So we have, just about 10 seconds left until the puzzle unlocks. Had that ready just in the nick of time. So we're riding the ferry right now. Let's see what today's challenge is. A storm came. Okay, we need to take evasive actions from a storm. Ship's navigation computer is malfunctioning. Produced extremely circuitous instructions. Okay. So we get navigational instructions as our input. Single character actions paired with integer input values. Okay. So north, south, east, west. Turn left, right, or right a certain number of degrees. Move forward by the given value in the direction that the ship is facing. So ship starts facing east. Only L and R actions change the direction the ship is facing. Okay. The ship's Manhattan distance. Okay, so we just need to apply all these instructions for our navigation sequence and then calculate the Manhattan distance where the ship ends up. So we will say let me go ahead and switch over to my coding window. So we'll make a position and heading struct that will represent where the ship is and what direction it's heading. We'll make an enum to represent the different headings, north, south, east, and west. So we'll start with east. And we'll go clockwise around the compass rose for the other directions. Okay, north. Okay. So for the position and heading, we have I forget which is latitude. I think latitude is east to west and longitude is north to south. So we'll say latitude, longitude, and if I have these backwards, well, it shouldn't matter for calculating the Manhattan distance. And heading equals. This will initially be k east. So then we will make a little function that just applies a step for our navigation directions. So we will say apply step. We've got our initial position and heading. And we will just pass that instruction as a string view. Make sure that we include the proper header to be able to use string view. There we go. So these are all going to be, these instructions are all going to be a single letter followed by a an unsigned number. So what I will do is we'll just use scanf to parse this. So we'll say we'll have a character to store direction. We'll have well, I'm going to make it an unsigned to store units. And then we will use our check function. We're going to put scanf inside our check function to make sure that we match all of the arguments that we give it. So we're going to check that we match exactly 2 for scanf, where in the parameters of scanf, the first one is going to be that string. And then for the format, we're going to have a character followed by an unsigned number, and that will be the whole of it. And then we will put the character into direction and the number into units. And then we just need to do something different depending on which character we have. So the possible actions that we have are, if we have north, we'll switch on direction. So if the case is north, then we will add to the longitude. We will say positive. I mean, this is not strictly how longitude works in the real world, but we'll say positive is north, negative is south. So we will say we'll add the units. South means just the opposite. So we'll subtract the number of units. We'll say east is positive, west is negative. So similar for east and west. Can put east, west, and do latitude for these. Now for L, we need to switch around the heading. So we can do this with another switch. We can also take advantage of the fact that that these are represented as integers underneath, and we can do this with some integer math too. So basically, if we make sure that these map to particular integer values, we don't have to write out that whole switch. So if so left means turning counterclockwise, so it's subtraction. So we'll just say if no, it should just be heading. If it's east, then it's 0, and we want to wrap around. And then we'll say that the heading is now north. Otherwise, we will just subtract 1 from the heading. And we have to, because these are strongly typed integers, we have to cast back and forth between the enums and the integers, but this will work. Famous last words, right? -1. Okay, if we have right, then it's, the mirror image of this, so of what we had for left. So if the heading is honestly, we can just do this, and if it goes over, we'll do modular division by 4 and take the remainder, and that will wrap around and give us exactly what we want. Okay, and the last case is if we have F, we move forward in the direction that the ship is currently facing. So we do based on the current heading. Oh, you know what? We got to have degrees for these, though, for left and right. Yes. So we'll say make a little helper function to calculate the new heading, because it might not always be 90 degrees that we turn. We could turn 180, 270, who knows how many. We'll make sure that degrees is a multiple of 90. And then so we'll subtract the number of 90-degree increments from degrees. And then we have to get it back into the canonical domain where it's between 0 and 3 inclusive. So we'll say while... This is not the fastest way to do it, but it's a simple way to do it. We'll just... And then turn right is going to be quite similar, but it's going to be even easier because if everything's all positive, modular division works exactly the way we want it to. So we do modular division by 4 to get it back into that range. And, oh, this should not be degrees. That should just be heading int in both of these cases. So, and very similar for the turn right case here. Now for forward, we switch on the heading cases, so we've got east. We've got all of our compass directions, so basically we do the same thing that we did for their respective cases up here, when we were just getting absolute directions. Yep, east, south, west, north. Maybe could have done this a little easier if I just consistently used either characters or this heading enum, but, you know, this is fine. It's slightly messy, but it's fine. So north is the last one. Okay. And then if we match nothing in here, the default should be check fail because it's not a valid navigation instruction as far as we know. So all we have to do is apply this repeatedly to all of our navigation instructions, and then we will get our final position, and we can calculate our Manhattan distance from our origin. So in the main function, first thing we will do is check that our number of arguments is expected, one for the program itself, one for the file name that we pass in. I need to include our I/O library here. There we go. Read lines from file, argv1. And then, so we start with, and this will default initialize to the origin facing east, which is how our ferry initially starts. And then we will just go through each of the instructions, applying the step, and then we will spit out the Manhattan distance, which is just the the sum of the absolute values of the latitude and the longitude. So we'll say, we can even just put this as like a little method in our struct. So we'll say sum the absolute values of those two. And that's what we'll spit out down here. Okay, I think we have our solution to part 1 now. So now we just need to make sure that we include add the dependencies on the proper libraries. What do you know? It's exactly the same as yesterday, so we can just copy and paste that in our build file. Let's go ahead and take just the simple little test example from the website and see how that works with our program. And just use that as a little check on ourselves. Okay, so it says 25. So we're good at least for that test input. Now let me download our actual input. Okay, let's see what it tells us. Okay, Manhattan distance of 858. Let's plug it in the website and see if we got it right. All right, first try. Going on to part 2. Before we can give the destination captain, you realize the actual action meanings were printed on the back of the instructions the whole time. So I actually move to a waypoint, which is relative to the ship's position. So we move a waypoint by north, south, east, or west. Left and right means to rotate the waypoint around the ship. And F means to move forward to the waypoint. I see. Okay, this is a little trickier. Okay. Waypoint starts 10 units east and 1 unit north relative to the ship. If the ship moves... Okay, waypoint is always relative to the ship. If the ship moves, the waypoint moves with it. Okay. F10 moves the waypoint. Moves the ship to the waypoint 10 times. Okay, so the ship moves whatever number of times by the delta to the waypoint. So if the waypoint is 10 units east and 4 units north, then to rotate 90 degrees, it becomes 4 units east, 10 units south. Okay. Okay, so this is a little bit more complicated. Okay, but I think we can handle this. So let's copy our part 1 solution over and use that to start part 2. Okay. So now this state here, these coordinates, are we need to represent both the absolute position of the ship and we need to represent the relative position of the waypoint. And I think the heading of the ship, if I'm not mistaken, is no longer important. So you can maybe even get rid of this. Yeah. So we'll say we'll have ship latitude and ship longitude. And then the relative waypoint latitude and longitude we will also put into this struct. Okay. I'm going to be doing something different with the turning. But, so now, we'll say coords, apply step, coords, similar stuff here. We'll parse the same directions, but now the meaning of them is going to be a little bit different. So n means move waypoint north by the given value. So that just means that waypoint longitude goes up for n. For south, waypoint longitude goes that way. For east, waypoint latitude moves. West, waypoint latitude moves. Okay, so for left and right, we rotate so a certain number of times. So let's see. So the example they gave was turning right. If you start with waypoint 10 east and 4 north, which in our case, and I'm just gonna like write this down in here in comments, what that would be. So 10 east and 4 north. If we turn right, then it becomes 4 east and 10 south. Okay. So we'll just say so for a 90-degree turn right, it looks like the longitude becomes the latitude, and the latitude flips to negative. It flips to the negative longitude, if I'm reading this correctly. So we'll put that. Flip that to the negative. And then, so we'll also have to do this for turning left. So I'm going to sketch a little diagram for myself here. Just let's say this one, so 2 comes north, east. Okay. Just wanted to visualize my intuition there. So I think this time it is, for turning left, it is the other direction that flips its sign. Just return coordinates. So east 1 at the latitude. Comes north 1. We have... Okay, yes, I think that is correct. And then, of course, we'll apply it however many times that we need to. So for left, we will check that, we will again check that the number of units is an even multiple of 90. And then we will just turn left however many times. For turning right, this is going to be very, very similar, except, of course, we're going to use the turn right function. And for going forwards, just however many times we will apply that delta that the waypoint represents to the actual coordinates of our ship. So we'll say for however many units of moving forward towards the waypoint, we are, you know what, we don't need to do it, actually do it that many times. I realized multiplication is a thing that we can do, and I realized we could do better with the turning too, but you know. Okay, we return that, and I think we now have a solution. Oh, we just have to change this to actually use the new new thing. And actually, the waypoint initially is not on top of the ship. It's not at 0, 0. I need to change what that initializes to. Can get rid of those comments that I was using while I was thinking about how to write the rotation functions. So the waypoint starts 10 units east and 1 unit north relative to the ship. Okay, so let's try it. Oh, and we need to put an entry for part 2 in our build file here. But we are just about ready to go with the part 2 solution, I think. So let's first run it on the test input and see what it gives us. 286. That's right, according to the website. Let's do it on the genuine puzzle input now. Okay, distance is 39,140. Let's see if we got it right. All right! Another puzzle successfully solved. Let's see where we are on personal stats. Okay, you know, under 2,000 for part 2. Not too bad, I'd say. I'm pretty happy with that. Yeah, so, you know, this was another fun puzzle. This one was pretty straightforward. It's just, you know, a little bit of spatial reasoning, moving around the grid. I guess the only thing in the solution that I'm not the most happy with is the stuff to turn left and turn right is a little bit clunky. At least like this turn left where we're just, you know, like, like, the modular arithmetic is a little clunky here. I didn't really want to think about, like, okay, if something is negative modulo, is that going to work right? And similar here for these turn left 90 and turn right 90 functions. Like, it's definitely, oh, well, I realize immediately that we only need to do units divided by 90, then modulo 4. In fact, why don't I just put that in here right now, because that's the most number of times that you would need to, because if you rotate 90 degrees 4 times, you're 360 and you're right back at the beginning. So that's an optimization that I see right away. Might as well do that here. And that should give us the same answer. Yes, it does. And at this point, since the most number of times we're going to apply either of these functions is 3 now, I am much less worried about like optimizing them for repeated application. So yeah, this was kind of just a simple navigation spatial reasoning puzzle. I think kind of an easy one, but this was fun to do. So I'm just about ready to finish up the stream now. As always, you can catch the replays of these live streams up on YouTube at my YouTube channel, youtube.com/spoonboy42. If you are watching one of those replays right now on YouTube, you can see the links down in the description to the daily Twitch live streams. No matter where you're watching this, I want to remind you that all the code does go up in my GitHub repository at github.com/Craig-Chasseur/AOC2020. You can see the repository on the screen right now. Once again, there will be a link to that repository in the description. Want to say thank you for everybody joining the stream tonight or watching the replays later. Really appreciate you watching. If you have any questions, feel free to drop them in the chat or the comments. And I look forward to seeing you again tomorrow night for another Advent of Code puzzle. Thanks for watching, everyone.